In this lesson, we're going to talk about alkenes and alkynes, which is a special type of hydrocarbons. Alkenes and alkynes are only a small percentage of the hydrocarbons in petroleum. However, they are very useful in making materials such as plastic. Alkenes and alkynes are considered unsaturated hydrocarbons. Alkenes have double bonds in them, whereas alkynes have triple bonds in them. They are unsaturated because they have fewer than the maximum number of hydrogens attached to them, and we'll see this in our general equations later on. Both alkenes and alkynes are very reactive with small diatomic molecules such as hydrogen and fluorine and chlorine. If they react with hydrogen, they undergo what's called hydrogenation, and if they undergo reactions with halogens, they undergo reactions called halogenation. When this type of reactions happen, you convert the unsaturated carbons into saturated ones, and you add hydrogen atoms or halogen atoms onto the double bond. As we mentioned, the general formula for alkenes is 2 hydrogens less than the general formula for alkanes. Therefore, the general formula is CnH2n. Here, N is 2, 3, or 4 because you cannot have an alkene with only one carbon atom. Again, alkene are hydrocarbons that have at least one double bond, and because all their bond polarities cancel, they are nonpolar. Even though the CH bond itself is polar, but they all cancel each other out. For example, ethene, the name ethene is ending in ene, and remember, eth is the prefix for 2 carbon compounds, so the general formula for ethene is C2H2. Here we see the structural formula for ethene. You have 2 carbons, and there's a double bond between those 2 carbons. And to fulfill the orbitals for the carbon atoms, each of those carbon atoms have to have 2 hydrogens to fulfill it. In the condensed structural formula, it's CH2 double bonded to another CH2. And in a line diagram, it is just 2 lines. Remember, each line represents 1 bond, so therefore 2 lines represents 2 bond or a double bond. A slightly more complex example is propene. Pro is the prefix for 3 carbon branches. Therefore, if we put into our general formula CnH2n, the formula for propene is C3H6. The structural formula has 3 carbon atoms, and there is a double bond in between 2 carbon atoms. And to fulfill the octet for all the carbon atoms, this carbon requires 2 additional hydrogens, this carbon requires 1 additional hydrogen, and the last carbon requires 3 additional hydrogens. In the condensed structural formula, we have CH2, double bond, CH, single bond to CH3. As for the line structural diagram, we have 2 lines here connected to a single line. For naming branched alkenes, we do it very similar to how we name branched alkanes. However, we add the location of the double bond at the end of the name in between the prefix and the ene. So for example, here we have 4-methyl-pentyl-2-ene. The 4 denotes the location of the methyl branch, and the pent indicates there are 5 carbon atoms in the main branch. The 2-ene tells you that the double bond is located between carbon 1 and 2. So therefore, if we were to draw this out, we would draw a main chain of 5 carbons, 3, 4, 5. The double bond is located between carbon 2 and 3, so carbon 2 and 3. And at position 4, there is a methyl group. 1, 2, 3, 4. There is a methyl group here. And we filled the other hydrogens so that they have each carbon has 8 electrons. So there should be 3 hydrogens here, 1 hydrogen here, 1 hydrogen here, 1 here, and 3 here. That will be the condensed structural formula for 4-methyl-pent-2-ene. So let's look at another example. The first thing you need to do to name a branched alkene is to identify the longest chain. So here we have the longest chain, and there are 6 carbons. We're going to have the double bond have the lowest number. We're going to give it the highest priority to have lowest number. So we're going to label this from right to left. So this is carbon 1, 2, 3, 4, 5, 6. We're then going to identify the branches. We note that there is a methyl group here at branch position 5 and another methyl group here at position 4. At position 4, there's also another ethyl group. So when we put the name together, we're going to put the methyl group first because E comes before M. So the name of this compound is 4-ethyl. And now we name the methyl branches. The methyl branches at positions 4 and 5. 4, 5 dash dimethyl, because there are 2 methyl branches. And our main chain is 6 carbon. The prefix for 6 carbon is hex. Hex. And we identify the location of a double bond at position 1, hex 1-ene. So this name is 4-ethyl-4,5-dimethyl hex 1-ene. Let's look at a couple more examples. Here we have 1, 2, 3, 4, 5, 6. A 6 carbon chain. Our double bond, if we're to label it left to right, it will be 1, 2, 3, 4, 5, 6. Our double bond will be between position 2 and 3. If we label it right to left, 1, 2, 3, 4, 5, 6, will be at position 4. Therefore, we're going to label it left to right, the green numbers, because that would give the double bond a higher priority or a lower number. We note that there is a methyl group here at position 4. So the full name of this compound is 4-methyl hex 2-ene. Let's look at another example. First, we have to identify the longest chain. One will be tempted to note this as the longest chain. It has 8 carbons in it. However, if we're to identify the longest chain using this method, this main chain here, there's actually 9 carbons in the main chain. We should be using the longest chain, therefore we're going to use the 9 carbon chain. So, a 9 carbon chain, let's number it. We're going to number it from left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's identify the branches. There are methyl groups here at position 7 and 3. So it is going to be 3,7-dimethyl. We note that there is a ethyl group at position 6. So 6-ethyl. Remember, ethyl comes before methyl because of its alphabet standing. And lastly, we note the position of the double bond at carbon 3 with 3-ene. So the name of this compound is 6-ethyl 3,7-dimethyl non-3-ene. Okay, let's now do the opposite. Let's draw a structural diagram given its name. Looking at the longest chain, we know that it's going to be a 6-carbon compound with a double bond at position 3. So 6 carbons, 1, 2, 3, 4, 5, 6, and a double bond between carbon 3 and 4. Let's look at the branches. We have 2 branches here at 3 and 5. 1, 2, 3, 4, 5. And they're both methyl groups. So H3 and CH3. And now we just fill in the rest of the carbons so that each carbon has 4 bonds or 8 electrons. It needs 3 hydrogens here, 2 hydrogens here. No hydrogen is needed at position 3 because it already has 4 bonds. 1 hydrogen here, 1 hydrogen here, and 3 hydrogens here. In previous lessons, we talked about structural isomers. Remember, structural isomers are compounds with the same formula, but they have a different structure. Now for alkenes, another type of structural isomer can also happen. These are called cis and trans isomers. Cis isomers are isomers that have branches on the same side of the double bond. Now this is only because the double bond cannot rotate. The atoms around the double bond cannot rotate. If this was a single bond here, this methyl group could rotate up or down quite freely. However, because it's a double bond, it cannot rotate. So therefore, this methyl group is fixed to the upper side of the double bond, as with this one. And because both of these methyl groups are on the same side of the double bond, we call this a cis isomer. In contrast to a cis isomer, where the carbon atoms are on the same side of the double bond, a trans isomer, the carbons are on a different side of the carbon double bond. So here we have one methyl group above the double bond, and here we have another methyl group below the double bond. These are across the double bond, so they're trans isomers. And the way to remember it is that on a trans-Canada highway, you go across the country, across Canada, and in a trans isomer, you would go across the double bond. Let's move on to the next type of hydrocarbons. The last type we're talking about is alkynes. And these are hydrocarbons with a triple bond. And because they have another bond, they have two fewer hydrogens. So therefore, their general formula is CnH2n minus 2. So let's look at an example. An ethyne. Eth is 2 carbons, and if we put it into the general formula, we get C2H2. Here is a structural formula for ethyne. You'll notice here that there are 3 lines here. There are 3 bonds between the carbon atoms. Here's a structural formula, condensed structural formula, sorry. And here in the line formula, there are just 3 lines between those 2 invisible carbon atoms. And here's propine. Again, you remember that prop is indicating there are 3 carbon atoms. And when you substitute n equals 3 into the general formula, you get C3H4. Here you'll notice there is a double bond between carbons 1 and 2 in the structural diagram, same as the condensed diagram. And in the line diagram, you have something like this. You could also draw this line diagram as 3 lines here and a bent line here. When we name alkynes, we use the same rules that we did for alkanes, except now we use the ending YNE instead of ENE. A twist comes up when we have a compound that has both double bonds and triple bonds. And the way we number the carbon atoms is to have the lowest number to either the carbon double bond or the carbon triple bond. However, if there is a tie, we're going to give priority to the double bond. And then when we name it, we're going to name the double bond first. So we're going to have the ene part and then the ine part. However, note we've dropped the E here just because of grammar. Let's do a few examples. Here in part A, let's identify the longest chain. Here we go. If we number left to right, we have 1, 2, 3, 4, 5, 6. If we number right to left, we have 1, 2, 3, 4, 5, 6. We will number right to left because the triple bond will be on position 2. So this is going to be a hex 2-ine, hex because there's 6 carbons. And the methyl branch falls at position number 5. So the full name of this compound is 5-methyl-hex-2-ine. The second example, once again, we have to identify the longest branch, the longest parent chain, and it is right here. And we will number this left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we note that the triple bond is between position 4 and 5. So the final name of this compound is some sort of dec 4-ine. Now we note where the branches are. We note there's a methyl group at position 7 and 8, and an ethyl group at position 6. Remember, when we name, ethyl comes before methyl because E comes before M in the alphabet. So the final name of this compound is 6-ethyl 7,8-dimethyl dec 4-ine. Here we have an example where a compound having a double bond and a triple bond. Both the double bond and the triple bond can be considered at position 1. However, to break the tie, we're going to give up priority to the double bond. So therefore, we're going to number this right to left, 3, 4, 5. So this becomes 1-pentene because we're going to denote the position of double bond being at position 1, and the position of the triple bond, is at position 4. Now let's go backwards. Let's draw a structure given the name. We have here, note the ending here is pent-1-ine, so we know there's a triple bond at position 1, and there are 5 carbons in the entire chain. 1, 2, 3, 4, 5. Triple bond at position 1. Now we know there's 3 ethyl, so put 1, 2, 3, CH2CH3. As well, there is a methyl group also at position 3, CH3. Now we fill in the blanks using hydrogen. There's 1 hydrogen here to give 8 electrons to the carbon atoms. This carbon does not require any hydrogens because it's already making 4 bonds. Similarly, this carbon has 4 bonds already. We need to add 2 hydrogens to this carbon atom to fulfill its octet, and 3 hydrogens on the very end. The next class of compound we're going to talk about are cycloalkenes. Alkenes again indicate there's going to be a double bond, and cyclo means the compound is cyclic or in a circle. So the general formula is CnH2n plus 2. This is for compounds with 1 double bond only. For each additional double bond that you have, you're going to lose 2 hydrogens. So the example here we have cyclobutene. Cyclo means again it's a circular compound. Bute means there are 4 carbon atoms, and ene we denote that there is 1 double bond here. It does not matter where the double bond is because you can rotate the cyclobutene compound and it will always be between carbon 1 and carbon 2. Here we have a very special example. It's called benzene. It is a 6-carbon cyclic compound, and there's double bonds all over, namely at positions 1, 3, 5, and 5. This is very special. This is a very stable compound. Usually cyclic compounds are not very stable, but because the double bonds are 1 apart from each other, they do something that's called hybridization, and their bonds all spread out or hybridize across the entire molecule. Benzene is a very stable compound. It is a very persistent pollutant in the environment. When we name a cyclic alkene, we're going to give highest priority to the double bond. Therefore, the double bond will always be positions 1 and 2. And then we name the branches according to the direction. In this diagram, this methyl group here is attached to position 3. So the name of this compound is 3-methyl-cyclohexene. Looking at another example, here we have a 4-carbon cyclohexene. 1, 2, 3, 4. So the name is cyclobutene. And we note that there is a ethyl group at position 1. So the full name of this compound is 1-ethyl-cyclobutene. Now let's go backwards and draw a structural diagram from a name. First we note that this is a cyclopentene. Therefore, we have a 5-carbon compound with a double bond between position 1 and 2. We also note that there is a methyl group, or there are 2 methyl groups, one at position 2, CH3, and one at position 3. For clarity, let's number the carbon atoms. 1, 2, 3, 4, 5. A term chemists use to describe unsaturated hydrocarbons is what's called the units of unsaturation. If you recall, alkanes, which are saturated hydrocarbons, have a general formula of CnH2n plus 2. These saturated compounds cannot hold additional hydrogens. They have the maximum number of hydrogen atoms. So then when we talk about alkenes, alkynes, or cycloalkanes or cycloalkenes, we know that they can hold additional hydrogens. So to determine how many units of unsaturation there are, which means we find how many pairs of hydrogens they can hold additionally. So to do that, we're going to find the number of hydrogen atoms as though they were saturated, and then find a difference. We're going to subtract between the maximum possible and the formula given to us, and then we're going to divide by 2, because we're really going to be interested in the pairs, or 2, of hydrogens that the hydrocarbon can hold additionally. So for example, C3H6. If we do the math, 2 times 3 plus 2, the maximum number of hydrogens that 3 carbon atoms can hold is 8. However, there's only 6 hydrogens here, so there's 2 missing hydrogens, and 2 is just 1 pair. So the degree of unsaturation for C3H6 is just 1. So far we've talked about alkanes, alkenes, and alkynes. These compounds are all considered to be aliphatics. Another type of hydrocarbons are what's called the aromatics. Now don't let the name fool you, these compounds do not smell very nice. In fact, they're very toxic. In fact, they're carcinogens. Now remember, benzene is a cyclic compound with 6 carbons, and there are 3 double bonds in there. And aromatic compounds have benzenes. You could also have a methyl group attached to it, that's called toluene. If there's an OH group attached to it, that's called phenol. But any compounds with this cyclic structure are considered aromatic compounds. Now benzene is unique because if we were to look at the structural diagram, we would expect to see 3 double bonds and 3 single bonds. However, when scientists look at these compounds using infrared spectroscopy, they can analyze the bonds present. They do not see 3 double bonds and 3 single bonds. They see a hybrid. They see 6 sort of 1.5 bonds. And it's because all 6 atoms share those double bonds together. Therefore, they're very reactive. We would expect that double bonds to be halogenated or hydrogenated very easily, but benzene does not hydrogenate or halogenate. They behave as though they're saturated compounds. They're very stable. Also, if we're to make a molecular model of a cyclic compound with 3 double bonds and 3 single bonds, you would get something very bent, sort of like that. However, in reality, benzene is a very flat molecule, and it's this flatness that determines its toxicity. Because of its flatness, it can get into DNA very well, and it can obstruct DNA replication and cause mutation, and that's why it is a carcinogen. So therefore, scientists, when they look at benzene, they say, okay, we can draw it with all those double bonds distributed around those 6 atoms. Therefore, this diagram here is actually a better representation of the electrons around benzene. Now, when we name benzene molecules or aromatic molecules, if there's one branch, no numbering is required, because automatically that would be at position 1, and we just do not write the invisible 1. However, if there are 2 branches present, there's going to be 3 structural isomers that are possible. Those 2 branches can connect at different atoms. And just as before, we're going to number the carbon atoms using the lowest numbers possible. Here we have an example of an aromatic molecule. It's a benzene ring with 2 methyl groups attached. If we label the first position as position 1, there's actually 2 additional places where the other methyl group can be attached to and cause different isomers. It can be attached to position 2 here, or it could be attached to position 3, or it could be attached to position 4. Now you're wondering, could it be attached to position 5? Yes, it would, but then it would just be a mirror image of the one at position 3. Therefore, we do not name aromatic molecules at position 5 and 6. You'll know that this is 1,2 isomer, this is the 1,3 isomer, and this is 1,4 isomer. In the classical naming system, we have what's called ortho, meta, or para. Those are the classical names, and you'll see that sometimes in your textbook. As an aside, sometimes the benzene ring can be considered as a branch. This is useful for really long chains. So for example, if we have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a 10 carbon chain, and let's say there is a benzene ring here. Instead of naming the 10 carbon chain as a branch of the benzene ring, we're going to name the benzene ring as a branch of the 10 carbon chain. When benzene ring is a branch, we're going to call a phenyl group. So therefore, this compound, we're going to call it a what is it, 1, 2, 3. So this would be 3-phenyl decane. Now let's name some regular aromatic compound. Here we note we have a benzene ring, and there are 3 branches, 2 methyl groups, and an ethyl group. The question becomes, where do we start numbering? Again, we're going to have a priority placed on the groups with the highest molecular weight. Here in this case, because there are 2 carbons and 5 hydrogens in the ethyl group, we're going to give it the highest priority. So we'll put this 1. And we're going to number clockwise because then we'll have the lowest numbers for the methyl branches. So here we have 1 ethyl, 2,4-dimethyl benzene. Let's now do an example where we're given a name and we have to draw the compound. Position 1 can be anywhere you want. We recommend that putting it at a branch location, and then numbering again can be done clockwise or counterclockwise, but we have to do it to give it the lowest number. Give the branches the lowest number. For 1-ethyl 3-methyl benzene, we're going to draw the benzene ring first. There's an electron distributed. 1-ethyl, so at carbon 1 we have CH2, CH3, and at position 3 we're going to have a methyl group. It's carbon 1, 2, 3, so we're going to draw a methyl group here. Here we number the carbon atoms in a counterclockwise position. However, you could have counted it clockwise and said this was 1, 2, 3, and you could have drawn your branch right here. However, these compounds are really the same because the red branch is really just a mirror image of the green branch. Therefore, we'll just erase that and have that as our final answer.